Say, this is basically an inaugural session of our lecture series. And today we will be talking about eye in the sky and beyond, remote sensing of Earth and other planets. Some of you may be a bit surprised. I don't know whether you got the input that the first lecture, which was supposed to be on launch vehicles, that could not happen due to certain unavoidable circumstances, and we have to start from remote sensing payloads or remote sensing of the Earth and planets. Uh, the way this lecture was structured was that we will build on the launch vehicles, but somehow we could not pursue with the launch vehicles. So I'll give just a brief, without any slides probably. I'll give you an idea, or if you want, I can run the slides also, as you please. You see 3-4 slides. It is like that we have, ISRO has 3 operational satellites: PSLV, GSLV Mark II, and GSLV Mark III. All these satellites are, as on today, launched from Satish Dhawan Space Center, that is in Andhra Pradesh, and it was up to now, it was Nellore district. I think now it has changed, but okay, the location remains same. That is only name change. So all the satellites are launched, and that location was selected in such a way that from this location we can launch satellites which are polar satellites, means which go from Earth's one pole to south pole to north pole, and north pole to go around the Earth or revolve around the Earth in a polar orbit. Or we can launch the satellites which are geostationary or geosynchronous, whatever you call them, which go around the equator or which travel around the equator. Now, the first of our launcher which we used, I am talking of operational launchers, not the experimental launchers, say our sounding rockets, then SLV, ASLV, they were all learning phase. But after that learning phase, we came to PSLV. And PSLV is basically a 4-stage rocket, which we have been using for a long time. And it is alternate liquid and solid. First stage is solid, second stage is liquid, third stage is solid, and fourth stage is liquid. And on around the first stage, there are 4 or 6 or whatever number of, depending on what type of capability you want, there are boosters, 4 or 6 boosters. So those are again solid boosters. Now this launch vehicle, which has different versions. Versions come only from, basically versions come from the number of the boosters that we attach to the rocket and the size or the size of the propellant loading in the boosters. All other 4 stages, which are main rocket, they are same. You can launch without even boosters. But that is how, as you go on increasing the number of boosters or their size, you are able to launch satellites with a higher and higher mass. Now, one of the versions, that is PSLV XL, that can launch about 1700 kg of payload in 600 kilometer polar orbit or sun synchronous polar orbit. We will learn what is sun synchronous polar orbit. Just remember the name. That is a orbit that goes around from pole to pole. So we can launch 1700 kg from 600 at a distance of 600 kilometer or at an orbit height of 600 kilometer. Or if we want to launch in, see, satellites are never launched in geostationary or geosynchronous orbit except for a couple of exceptions. Otherwise, they are always launched in what is called GTO or sub-GTO. That means it is an elliptical orbit with farthest point which is very near to the geosynchronous orbit, that is about 35,800 kilometers, and the nearest point is about 250 kilometers. That is perigee, what we call nearest point we call perigee. It is about 250 kilometers. and the farthest point is the apogee, what we call, and it is at about 36,000 kilometers. So that is how we are able to launch. That is what the capability of this launcher is there. Then if we go next, then we have okay, in this I will tell you an interesting. Up to now we have launched 53. That is why we are calling it our workhorse. We have launched 53 PSLV different versions. Out of that, there was one failure in the beginning and one more failure in between recently that occurred, and that is when we were launching our IRNSS or Navik, that some failure occurred, and one partial failure. So if you consider everything, out of 53, we have 2 failures and 1 partial failure. So it is an excellent record of any launch vehicle operator in the world. So that is the thing. Other thing what we are is our is GSLV Mark II. GSLV Mark II has had total 14 flights. Out of that, almost I think 5 or 6 flights, I don't remember the exact number, 5 or 6 flights have failed or partially failed, and remaining flights have been successful. This is not a very good success rate, but using this GSLV Mark II, we learned couple of things. Because you want to, why, if our PSLV was working so well, why would we launch, why would we have another launcher which is GSLV? The reason is that the GSLV can launch up to GSLV Mark II can launch up to almost 2 ton, slightly more than 2 ton in GTO. So that other fellow, our this PSLV cannot do. So it is 2 ton in GTO. That is what we were capable of doing. And main thing about this launcher is we have our own cryo stage. Cryogenic stage means it uses liquids which are cryogenically cooled, means less than around 150 to 100 K, somewhere 100 to 150 K or even lesser than that. So okay, they are, see, you can see liquid oxygen and liquid hydrogen. So those are very, very cool liquids. So we put those liquids, and when we use those liquids, they are very energetic liquids, so we can get much more thrust per kg of the fuel that we use. And if we have to launch satellites to a higher orbit or with heavier mass, then we have to have cryogenic stage, and we developed our 7-ton cryogenic. 7 ton means that is the thrust that it provides. 7-ton cryogenic stage for GSLV, but it is a mixed result. But I will tell you another interesting thing, that we have GSLV Mark III, and GSLV Mark III, its capability is 5 ton in GTO, that it can put 5 ton in geosynchronous transfer orbit, which I told you that it is an elliptical orbit with perigee at about 250 kilometer, 300 kilometer, and apogee at 36,000 kilometer. It is called geosynchronous transfer orbit, because that is an orbit which is an elliptical orbit. Then you launch the satellite in that orbit, and afterwards, using the satellite's own engine, you can circularize that orbit and convert it into a geosynchronous or geostationary orbit, as you call it. So that it can launch 5 ton. Of course, as on today, we have had, I think, 4 flights today, and maximum we have launched our Chandrayaan 2, GSAT-19, GSAT-29, all were launched on GSLV Mark III. And the first one, which we wanted to try out and find out, it did not contain the cryo stage, but without cryo stage we launched. And in that, if you remember, what care module was there, that is crew module and atmospheric re-entry. Means we want to send our Gaganyaan. So for when we send Gaganyaan type of satellites or launch them, then we have to bring our astronauts back. And for bringing back astronauts, you need atmospheric re-entry. Means it should come, and without getting destroyed, it is coming at a very fast speed. At that fast speed, without burning down, without happening anything, it should come down at that speed. When it comes down, when it starts, the speed is about 8 kilometers per second. You can convert it to meters. 8 kilometers per second, you can convert it to kilometer per hour by multiplying by 3600. So that is the speed. But when it lands, your speed is very, when it lands, it is very 1 meter per second or 1.5 meter per second. So you have to slow down that fast in a short duration, and that too without giving larger G forces on the astronauts, or burning down because of the friction, burning down our module which is coming down. So that was also launched by this. These are the things, and the last one is that this GSLV Mark III has a 20-ton cryogenic storage. So it is a very powerful stage. As on today, we have launched up to about 4 ton in Geo transfer orbit or Chandrayaan type of orbit. Chandrayaan की जो initial orbit थी उतना, लेकिन finally we want to take it to 5 ton in GTO or 10 ton in low Earth orbit, and our Gaganyaan will be launched in GSLV Mark III. Now, with this introduction, what I want to start is that I want to start our main course, because unless you understand this, you will not be able to appreciate what we are going to talk now, our main talk. So it is starting late by another 10-15 minutes. Initially, it was 10 minutes late, and I will try to Are you able to see the screen?
No, sir, not yet.
Is it?
No, sir. No, sir, not yet to me. Is it visible to you, Akanksha?
No, screen is not yet visible.
Okay, let me see. Why it is not share? Your screen is coming, but it is not sharing. Now, present now. It says window or entire screen?
Entire screen, sir.
I did entire screen only, but then.
Sir,
Sir,
please click on that screen. A small window will come where entire screen is present. So click on that screen and then share.
when that box will open, no, sir, click on that screen window and then a blue button will appear as share in bottom.
Did you see that now?
Yes, sir, it is being presented now.
Okay, good.
Yes,
So
sir, just click the hide button over there, sir.
Hide button? I don't see hide button there.
Yes, that only.
Okay. Are you able to see?
Yes, sir, yes.
So shall I make it full screen?
Yes, sir.
And now it is full screen. Are you able to see the full screen?
Yes, sir, it is visible now. Please
Okay.
continue, sir.
So now we
Hello.
see. Hello.
Before we start, I would like to mention that our HOD Shilpa Sonkar ma'am is also present over here. Hello, ma'am.
Okay.
Thank you
Hello. Good evening. Good evening, Shilpa ji.
Good evening, sir.
Nice to meet you online.
Yes, nice to meet you too online, sir. And it is a great pleasure that first time, first of its kind, we are having such a workshop for our students, and it's a great pleasure to us, sir.
Oh, so nice of you. Let us see whether it continues to be pleasure when I end it.
Definitely, sir. Definitely, our students are going to have good takeaways, sir.
Yeah. Yes. They can keep their questions with them and ask me at the end of the lecture. It is little longish, but let us see how much patience all of us have. And if we lose the patience, please raise your hand and we will stop at that location.
Yes.
See here, I am giving a glimpse of what type of remote sensing satellites we have launched, where we started and where we are today. In remote sensing satellites, we have two type of satellites. One is our satellites which are there, which we are using for our resources. So resources means say agriculture, water, then cartography. So those satellites are at about their orbit is about 500, 600 kilometer or maybe even 700 kilometer from the surface of the Earth. It is a circular orbit and it is a polar orbit. Why polar orbit is there? Because when you have a polar orbit, what happens is the satellite is going from north to south and south to north, while below that Earth is moving from west to east. So all the parts of the Earth at some time or other will come under the satellite and you can take a picture. So all our remote sensing satellites have are polar satellites. They are sun synchronous, that we will see little later as we go. So except that initially when we started our Bhaskara 1, Bhaskara 2, Bhaskara 1, they were mostly experimental satellites, and those satellites were not sun synchronous, or they were not polar. It was about 50-degree incline to the equatorial plane. So now why I gave you the introduction of the launchers. Suppose somebody decides that we launch a satellite from a gun. Here you are seeing a gun which is launching a satellite, okay, or it is trying to launch a satellite. But when we are releasing an object from the gun, it is not a satellite, but it is a projectile. So we have to understand the difference between satellite and projectile. In projectile, what you are doing is that most of its velocity, or what you call impulse, that you are giving in the beginning. After that, it is a free flight under gravity, and as long as you are in atmosphere drag and gravity. But assuming that there is no atmosphere, it is only moving under the gravity. So depending on at what speed we send it, it will be falling very near to the Earth or very far from the Earth. But if you do the calculations of how much force we have to apply, and that to go it round the Earth, so that the curvature of the Earth is such that when your vehicle starts curving, Earth's curvature and this, they coincide, they go down equally, so then it will become a satellite. But for that you will need a very high initial impulse, and if you give that type of impulse in the beginning, what will happen is that either your satellite will break, or the type of impulse supply which you need will be so large that building them will be unwieldy. So you cannot launch as on today. It may finally come as on today with available propellants. Propellants means fuels and oxidizers. Available fuels, we cannot launch a satellite using a projectile type of motion. Now here, if you see on the left, what you are saying is that, you see, when we are releasing a satellite through our launch vehicle, okay, launch vehicle is not simply releasing it wherever it is. Suppose our launch vehicle, normally all the satellites are released at the lowest point, where the lowest point of their orbit, that is called, we call it perigee. So you release at perigee, whether it is geosynchronous geostationary satellite, or whether it is a remote sensing satellite. But for remote sensing satellites, our perigee and apogee, because it is a circular orbit, they are same. So you release it at 500, 600 kilometers, but it is a circular orbit, but still it is perigee. Or it can be sometimes apogee also. I will. Why I am telling it perigee is that there is a reason. It can be apogee also. But the way you are releasing it, such a way that if you just release it, the satellite will come down. It will not remain there. The reason is that gravitational force is pulling it down. And once gravitational force is pulling down, it cannot remain. You can see here on the left side. But if you want to put it in an orbit, then you have to give a horizontal velocity also, or tangential velocity as they call it correctly. So you have sufficient tangential velocity. Now I will talk in engineering terms rather than physics term. So tangential velocity, when a vehicle is moving with some tangential velocity, it is experiencing some centrifugal force, the force which is trying to throw it away from the center of the Earth, and that is mv square by r, correct? That is the centrifugal force, and the Earth is pulling it down with because of gravitation, and that force is m mass of Earth multiplied by g, that is gravitational universal gravitational constant, multiplied by the mass of the satellite, and then divide by r square. So where the satellite will go, you balance these two forces, centrifugal force, so you will get a value of r. So depending on what velocity you have given, it will go in that orbit r, because r and v will be fixed automatically. Once r and v are fixed, means period is fixed, height is fixed. R is height, so period and r will be fixed. So if I want to launch in a particular orbit, I have to give a given velocity by our launch vehicle, and that is why, because we have different type of launchers, they have to give, we have a given payload, and to that or given satellite which has a particular mass. Now I have to give that much velocity, tangential velocity. First I have to take it there up to a height where I want to release the satellite, and then give a tangential. Of course both of these things are happening simultaneously, but let us, for understanding purpose, let us say that once we are going up to say 500 kilometer or 250 kilometer, and then you are giving a tangential velocity so that it will go around the Earth. So our launcher should be capable of giving that much tangential velocity to the satellite which has a particular mass, and that is why, because it doesn't have that capacity, it will not be able to launch, and the satellite will come down. Now here you can see now how satellite does it. See, satellite, what type of velocity it has to give. How do you determine in which orbit satellite will? Suppose I have given some velocity, then it may go to any orbit. So that is not so arbitrary. Here you can see at the bottom there is an equation which says that now for a given orbit, E is eccentricity of the orbit. It is an ellipse, let us assume. So if that ellipse, let us assume first that ellipse eccentricity is 0. I want only circular orbit. Circular orbit means this 1 plus E term in the bracket will vanish. So for a circular orbit, I will give a velocity v, which is equal to gravitational constant into mass of the Earth divided by the perigee radius. That I have to give. If I give that much velocity, then it will be in a circular orbit for a given perigee radius. But if I want some eccentricity, I put that eccentricity. How do I determine? It is very simple. Say you say your ellipse. All of you know how to find eccentricity. So from that you find the eccentricity. Put that eccentricity means how far you want your apogee, how far you want your perigee. So apogee minus apogee means you have to consider from the center of the Earth. Apogee minus perigee plus apogee plus perigee, and this you are considering from the center of the Earth, not from the surface of the Earth. So from that I determine what is the eccentricity I need for a given type of orbit, and then I give calculate the velocity, and by releasing the satellite out, I give that much value. So if I give, suppose, a velocity which is E is 0, then I will go in the circle like this. I give higher velocity, then it will be an ellipse. I give much higher velocity, then it may be an escape velocity. I can make it parabola or hyperbola. Means it will never return to Earth. So that type of thing you can do simply by deciding the height at which you are releasing, and at that height what type of velocity you are giving. Now you can have here, you can see different type of orbit. This is a very elongated orbit, okay, and this is called highly elliptical orbit. Then you have slightly lower elliptical orbit, but this is almost a polar orbit type of thing, and this is our geostationary orbit. See, these are the diverse orbits, and I have not drawn here all the orbits, but we will go through those things little by little. Now, how do you determine, or how orbit is defined? That we have to understand. See, orbit is defined. Let us say that I want to define an ellipse. What parameters I need of ellipse? I need eccentricity and semi-major axis. So if two parameters are there, I can define an ellipse. So I have defined the satellite's orbit. Now I want to put that orbit in a plane around the Earth. How do I do that? I again need two parameters. That plane here, you can see yellow plane, is inclined at an inclination of I. Okay, and that inclination is with respect to the equatorial plane. So I need I, and I need where it will intersect, these two planes, where they will intersect. Of course, they intersect in a line, but if you see the exact orbit, because it is not a plane, actually it is an orbit, it will be 2 points. One point is where the satellite is going from below the equatorial plane to above the equatorial plane, means from south to north, and that is called ascending node. And other point is from north to south it is going, and that is called descending node. So if I say I define an inertial direction in space and tell that my point of intersection is so many degrees from that inertial reference which I have given. I will not go into how it is very simple to define an inertial reference frame. So then I need two parameters, that is ascending node and the inclination. So now I have defined a plane. So I can now put my orbit in that plane. Once I put my orbit in that plane, okay, now I want another thing to know, and that is how to see. I can rotate I can rotate my orbital plane anyway in this plane, the plane which I have defined. I can rotate anyway. So where it will be rotated, what will be the, so then I have defined argument of perigee. That means where the perigee will be there with respect to the line which is joining ascending node and descending node, and that angle you are measuring in the orbital plane. So that is my argument of perigee. So now I have fixed the ellipse. So I have defined ellipse, I have defined the plane in which I am keeping the ellipse, and I have fixed the ellipse in the plane. So these three things have happened. Now to know the position of the satellite, I know true anomaly, which indicates the position of the satellite. So these are called orbital element or Keplerian element, which many of you would have learned, but I thought that we should understand the significance of 6 parameters. Then we don't have to remember those parameters. You will automatically know that you need 2 parameters for defining ellipse, 2 parameters for putting a plane with respect to our equatorial plane, 1 parameter to fix the location of the ellipse in the plane, and 1 parameter to find the define the location of satellite in the orbital plane. That is how we define Keplerian elements. Now here I am telling what type of orbits the satellites are normally put. LEO, that is low Earth orbit. Low Earth orbit, what you are doing is that low Earth orbit can be, you see, we are telling low Earth orbit, so it is less than 1,000 kilometer orbit around the Earth. That is from the surface of the Earth. Now it may make any, as long as I am not giving any condition on the orbit, it can be in any plane. So it can make any inclination with respect, it can be even 0 inclination, or it can be 90 degree, 97 degree, other way around you go all the way. It can be any inclination, and that is called low Earth orbit. And then you define what is its inclination, what is orbit height, or what is the height of, suppose if it is an elliptical orbit, then you have to define both apogee and perigee. If it is a circular orbit, you define only the radius. But then we have SSO. Now what is SSO? That is Sun Synchronous Orbit. Now why do you need this type of orbits? Most of the remote sensing satellites need this type of orbit. The reason is that when on whichever location you are taking picture, a satellite is suppose exactly overhead over Ahmedabad, or for that matter Pune or Bangalore, that always see it will come at any location 2 times, any given location 2 times a day. Not every day, but whenever it comes, it will come 2 times. So whenever it comes on a given latitude, the time will be same. So we define the latitude time of equator. So equator crossing time. So equator crossing time will always be same throughout the year. It will always cross equator from south to north, that is ascending node, or north to south, descending node, whichever we have defined. It will always go. Now for doing that, what you need? What you need is that the plane of orbital plane actually rotates. Orbital plane itself rotates around the, say almost around, because it is a polar orbit, it will rotate around the axis of the Earth, more or less. Of course, its own axis, but its own axis is right now very similar to north-south, our pole-to-pole axis. It rotates. Now you control the rotation. Here, you see delta, and how the rotation is defined. Ascending node. You see, ascending node we have defined, if you remember, that is omega. So omega is where orbital plane is intersecting the equatorial plane. That location goes on changing. Now, if you change that location, what happens is that time changes. But what I am doing is that now every day Earth goes around the sun by about 1 degree. That exactly we are not talking, but about 1 degree, 360 degrees and 365 days, so about 1 degree. So you make this plane also rotate 1 degree per day. Now here the rotation of the plane is given. So how it will rotate. So there is a given inclination. All other parameters, suppose they are fixed. If other parameters are fixed, that is because you want to launch in a particular orbit. You have a particular say even its momentum is given. So all those things, other things, let us say they are fixed. Now only parameter, two parameters which are under your control are inclination and orbit height, RE. No, not RE, P square. P square and R, cos I and P square. These are the two parameters. So means I want to put at what orbit height and what inclination. So there are pairs, these pairs. If you launch a satellite with that pair of inclination and the orbit height, then it will become sun synchronous, so that you will take pictures under the same illumination condition. Of course, over the year, sun goes from north to south. That you are not correcting, but that is a very slow motion. So from day to day, you can compare your picture without much of a problem. Illumination conditions will remain same. That is why we use SSO. Then there are middle Earth orbits. You know, all of us, you know that GPS. All GPS satellites are in middle Earth orbit, and they are at about 20,000 kilometers from the surface of the Earth. That is because they are in different planes, and they have put it in such a way that at any given location you will be seeing minimum of 4 satellites in good configuration. Good configuration means what? They are not one, either they are not together, all 4 of them, or one is at horizon and other is at middle, and so otherwise it will be difficult. So in good configuration, what they call DOP. So they put in a different orbit, different planes. About 6 planes are there. In each plane, some 6 or 7 satellites are there. And those satellites are such that with having a 4 satellite, receiving data from 4 satellites together, using that data, your receiver can calculate its position. Remember, GPS never knows the position of your location. Only the receiver knows, because the position is calculated by the receiver. Not otherwise, it will be chaotic. They are sending the data. Now, because see, if I want to know my position, I need 3 parameters. What are the parameters? Latitude, longitude, and altitude. So I need only 3 satellites, because 3 unknown, 3 equation. But 4th is that because there is some time error also, because time on the ground, which is of course you are synchronizing your receiver, but receiver is not fully synchronized. All satellites are also not. So there will be a delta time. So 4th is delta time. So these 4 parameter, you generate 4 equations, solve those 4 equations. You know the satellite from the satellite data which is sending. You know the range of the satellite. Knowing the range of the satellite, that is R square. R square is, you assume the parameters of your location, and then x1 minus x2 whole square plus y1 minus y2 whole square and z1 minus z2 whole square. Solve that equation and you will get your location. That is, of course, it is slightly complex. I am simplifying it. So these satellites are in MEO satellite, that is middle Earth orbit. That is the way they have done is that number of satellites and the power they want to transmit, you have to do a trade-off. And doing that trade-off, they found that this is the best way of doing, particularly when you want to cover the whole world. Then there is another orbit which is called Molniya Orbit. But before I go to Molniya Orbit, I made a mistake. I should have gone to Geo Orbit. Here, Geo Orbit is which, because what is happening, all our communication satellites are in geosynchronous Earth orbit. That is means they are at 36,000 kilometers, or whatever number you see is 35,786. I call it 36,000 for, it doesn't matter for our discussion. and it is an equatorial orbit, means it goes around the equator at 35,000. Now, as I told you, that at a given radius of the orbit, the satellite has a particular velocity, angular velocity or tangential linear velocity, whichever, because r omega is tangential velocity and omega is angular. Now you place, as you go on changing the orbit, your tangential velocity changes. So at 35,000 kilometer, 36,000 kilometer, your angular velocity is same as that of the Earth's angular velocity. That is 1 degree per whatever that in 24 hours 360 degrees. So it also goes around Earth in 360 degree. It covers in 24 hours. So from any location, that satellite will appear stationary to you. Now, advantage of this type of communication, you don't want to cover all Earth here. See, because from any given location, you will be able to see about 1/3 of the Earth. Only thing is that because this is on equator, if you draw a tangent to the pole, it will not go up to the pole. It will be going up to 81 degree if you draw a tangent, and it will be seeing, and both north. So beyond 81 degree, both on North Pole and South Pole, you will not be able to do the communication very well using this type of geostationary satellite, because you don't want to move your antenna. So all communications, let us assume that Tata Sky or Airtel or whatever they are, suppose when they Dish TV, or every time you have to move your antenna, it will be chaotic. And because they cannot keep beam very large, they keep narrow beam, because if beam large means your power goes down. Your power goes down means you need larger antenna. So beam is very narrow. So all the energy is concentrated in a smaller beam. Because it is a smaller beam, many of you must have seen, if my satellite, that dish at my terrace moves little bit, its signal will be lost. So, and you don't want to go on moving that. So to do that, it has to be in geostationary orbit. Now, as I told you, geostationary orbit has one limitation. It is a very slant orbit as you go away from the equator. So lot of loss is there. Loss is almost proportional, if I remember right, proportional to the r square, the distance, that is range square. So as you go away from equator, range becomes larger and larger, and signal becomes poorer. But Russia, the problem with Russia is that its entire Russian region is very much on the north and up to the North Pole, Arctic. Now, they cannot use these satellites very effectively. So they found out another method, that is use this orbit which is called Molniya orbit. That is why I thought GEO should have been first. So Molniya orbit. It is an orbit which is inclined at 63.4 degree with respect to equator. It is a 12-hour orbit, and that orbit is such that farthest point is about 40,000 kilometers. So satellite dwells at that location very long time, because it is a 12-hour orbit, and because it is almost on the equator, on the pole, North Pole. Now, so two conditions are there, that this plane should not. I told you that plane goes on rotating, omega. So you don't want it to rotate. If I don't want to rotate, I have given the equation. You solve that equation for zero rotation. So omega dot. Omega dot 0 means I will need say 360 degrees. Just 1 minute. Just a minute. So I will need 63.4 degree. If I put at 63 my orbit will not rotate in the same plane. So north side of the farthest side, apogee will always remain on Russia. And other thing is that I make it a 12-hour orbit. So it will go and come back at the same location after. So if 2 satellites I put, then it will be good enough. I will have to move my antenna very little, because as per Kepler's law, remember, equal area in equal time. So because now what happened for equal area, here my arm length is very large. So movement of the satellite is almost zero. There is little bit of movement, but almost zero. So you can keep your antenna, they can afford to keep wider beam, because what happens is that your only covering this much area. You don't want to cover other things with this. So they use, many of them use this type of orbits. Now we have seen types of orbit which are used. Now in our remote sensing satellite, we use both sun synchronous orbit and geostationary orbit. You will think that why we use two types of orbit. See, sun synchronous orbits have some advantages. You see, what is the see, orbit determines what part of the globe you are viewing. So if I have sun synchronous orbit, as we discussed, I can view any part of the earth, because I am going from north to south, earth is moving from west to south, west to east. So every part of the earth will come under the satellite at some time or other. So a sun synchronous will allow that. Then if I put at a very large distance, that means I put R very large, then what will happen is that I will be able to see a very small area at any given time. Not only that, for my for a given angular resolution, means what angle my sensor sees on the ground, that will become large. So I will not be able to see the details. So I cannot see the details. But on the contrary, if I am at 500 kilometers, 600 kilometers, for a given angular result, I will show you what happens is afterward. So for same FOV, if I were very farther, that is angular FOV, I was very far, then I will be able to see only sketchy details on the ground. But I am at 500, 600 kilometers. You will think, why not 100 kilometers then? You never ask that, because you remember today what happened. How many of you remember of Elon Musk's Starlink satellites? See, Elon Musk 40 satellites were burned today. More or less, they were burned. I mean, all of them have not come down, but they have become defunct. What happened is that there was a magnetic storm. That magnetic storm, what it did, it heated up the atmosphere. Those satellites were there. 49 satellites that they had launched on 3rd of February. Those satellites were only at about 200 kilometer orbit. Our atmosphere, because of this geomagnetic storm from the sun or coronal mass ejection, because of that, what happened is that our atmosphere got heated up and it went up. When you heat up, your atmosphere expands. So it went up to 200 kilometers. They tried to stop it, but they could not do it. They tried to go to safe mode. And 40 of their 49 satellites were lost. So you cannot put very low, otherwise this is what will happen. So you have to put satellite, even our International Space Station, it is at about 400 kilometers. Even without or with geomagnetic storm, it comes down about every 15 days, it comes down about 20, 25, 30 kilometers. So they have to lift up continuously. But because people are visiting there, you can afford to do that. You can go on filling the petrol like what we are doing in our car. But if it is a satellite which doesn't have people on that, and it is you are not accessing it any other time, you cannot afford, so you have to put at a slightly higher. So 500 to 700 kilometer, less than 1000 kilometer orbit is ideal for remote sensing satellite. But the coverage, that is, suppose I have gone to, I told you that this, any part of the satellite, given part of the satellite will come under, part of the earth will come under the satellite sometime or other. Now that sometime or other, it is not always, I am not seeing that part. I have to, that is called revisit. I have seen this part today. After how many days I will see the same part again? That is revisit. So revisit is not very good. Here it can be 5 days, 10 days, 15 days. But sometimes you can, if I don't want to see other areas, I can tilt my satellite and see within 1 or 2 days. But still at a cost, that is because I am not seeing some other areas which may be important. But you have to live with it because it is a trade-off. And then what happens is that the satellite remains continuously, one side is continuously illuminated, other side is night side. So you can do calibration of the satellite and it goes around Earth in about 100 minutes. So it's very fast. After 100 minutes, almost for 50 minutes are available to you for taking pictures. This shows, this is a polar satellite. You can see Earth is moving, going from west to east, and here it is slightly tilted wrong way around, but west to east it should go. And what happens is that nearly constant illumination is occurring because of the polar sun synchronous orbit. Better spatial resolution you are getting, as I told you. Global coverage is possible because, and this, but what happens is that because it is still near 7,000 to 700 to 1,000 kilometers. So what happens is that its life is not very much. Life is mostly determined by the fuel that you can load in the satellite. So anyhow, you have to do some correction, and in the correction you lose lot many fluids. And when you lose the fluids or propellants, what we call, or fuel, what we call, and then it doesn't. Now that is okay. But suppose for weather, I am not interested in very small details. What I am interested in is that details may not be as good, but I want to cover a larger area and I want to see that area repetitively. All our weather satellites, you must have heard the name of Kalpana weather satellite, INSET 3D, or every day you must be seeing pictures by IMD when that tornado or what we call hurricane is there, how it is moving, where it will go. All those details are obtained from our INSET 3D and 3DR satellite. Of course, now earlier it was Kalpana, but Kalpana lived for a very long time. Now it has been put to rest. So now what happens is those satellites, they can take a picture of the given portion of 1/3. You have put it over India, India center. So 1/3 of the globe, of course, not covering fully your North Pole and South Pole, 81 degrees South Pole to 1 degree North Pole. That much area, and in this also 81 to 81 degree east-west also. So that much, about it will become about 1/3 of the area of the Earth. You can continuously see and you can take picture with our INSET series of satellites every half an hour. Resolution is not good, but it is continuously available. Not only that, I can change the scanning of INSET 3D mirror such that a given area, suppose I am concentrating on a hurricane, then I can if that hurricane or whatever name you are giving, that if I want to see only a small area, I can reduce my scan, and every 5 minutes I can scan that area of say 400 kilometer by 400 kilometer or 200 every 4-5 minutes I can see, and I can track it how it is moving. So that is the advantage of geostationary orbit, particularly for weather. Not only that, I can get from the INSET 3D series of satellite, I can get the wind velocity, I can get the cloud motion, I can see even humidity, I can measure the ozone. So continuously I can make those measurements using my, and those are very frequent measurement. Every 2 hour, 3 hour, I can get full measurement. Those are useful for weather prediction. So for weather, whatever weather predictions you are seeing, those are happening not only from the satellite, but lot of data from the satellite goes into the weather prediction model. So we are using that. Now we will try to understand how the remote sensing satellite works. Finally, remote sensing satellites. When you are tired, please tell me, Atharva and Santosh ji. We can stop for some time and we can start again.
Okay, sir. Okay, whatever you feel comfortable, sir.
Right now it is okay. I will tell
Yes,
you.
sir. Yes.
So
Yes,
see, finally, what we are measuring is radiation. Now, as you all know by Planck's law, the radiation, the peak of the radiation, as the temperature of a body increases, the peak of the radiation shifts towards the lower wavelength or higher frequency. So see, and you can find out, see let us see the bulb. I apply a very little voltage to the bulb. Bulb will appear red. Then I go on applying higher, more and more voltage, it becomes white. That means it is a spectrum, or spectrum means the content, frequency content or wavelength content or color content changes. So here we can see now for our eye, total if you see electromagnetic spectrum, that is the electromagnetic waves. It goes from all the way from cosmic rays, which are very low wavelength. That is, you can see here X-rays. Everybody knows X-ray. It is about 1 to 4 angstrom. Now 1 angstrom is 1 raised to 1 into 10 raised to minus 10 meter. That is 1/10 of a nanometer. So about 3-4 nanometer. 4 nanometer, I mean 4.4 nanometer X-ray is called soft X-ray, while 1 nanometer, 1 angstrom X-ray is called hard X-ray. So all our medical, mostly they use 1 angstrom type of X-rays. So starting from X-rays to 100 meter, that radio wave, you have this full spectrum. Out of that full spectrum, only from 0.4 micron, that is 400 nanometer, to 0.7 micron, that is 700 nanometer, our eye can see. But we can put sensors which can see over entire this wavelength. That is the capability of the sensors. Not only that, we are making all the measurement now on the ground. I will not go into this slide because it again repeats where what is the frequency of microwave, what is the wavelength of micro, what is the wavelength of infrared, what is the wavelength of visible, ultraviolet. Ultraviolet, of course, as you know, is from almost 100 nanometer to 400 nanometer, just less than our blue light. So, sorry, this I will not repeat. Now, I will tell you an inter. Now, when I am making measurement, say from a satellite off the ground, I have two things. One is that I have the solar reflected radiance. That is how radiance means. I am calling it a spectral radiance. Spectral radiance means what I am telling is that it is with respect to wavelength or with respect to color. So this is what I see reflected radiance from the ground. That is, sun is illuminating the ground. It passes through the atmosphere. Of course, I have not here included atmospheric effects, but suppose on the top of atmosphere, this will be the radiance that I will be able to measure at each wavelength, which is total about 1300 watt per meter square type of thing. And then Earth is at about 23 degrees centigrade, 25 degrees centigrade. So it is also radiating. So it is emitting. So that is the emitted radiation of the Earth. Now, if you see clearly, at about 4.5 micrometer wavelength, the emitted radiance of the Earth increases much more or is much more than the solar radiance. So I can suppose I am I want to see anything what is reflected radiance. I can see about 1.5, 2 micron, 2.5 micron. Beyond that, the radiance which is coming from the Earth will mix up with it, and I will not know whether it is sun's reflected energy or Earth's emitted energy, and both will have a different characteristic. Suppose there is one target is radiating also, and it is reflecting also. So in this region there will be a confusion. So to avoid that confusion, what you do is that when I am making a measurement in this radiance, in this measurement, say from 3 micron to 6-7 micron, those, if I want to measure the Earth radiance, I will make those measurements at night because there is no sun. And if I want to make the measurement of the sun, only reflected radiance, it is very difficult to plan. So I normally make emitted radiance about say 3 micron to 5-6 micron. I will be making those measurements at night. Of course, finally at night, if I am making measurement at 10 micron, 12 micron, that is you are measuring infrared radiation or heat you are measuring. So that I can do either daytime or nighttime. So many of our instruments are, some of them are operating in this region, many of them are operating in visible region, and some of them are operating in, depending on what you want to measure, your measurement wavelength will change, or what is my target, what I want to understand, what parameter I want to divide. Depending on that, I will decide where I will make the measurement, in which color I will make the measurement, or at what wavelength I will make the measurement. Now, when I make the measurement, as I told you that in the previous slide, I told you that sun's reflected energy and Earth's emitted energy, but that is above the atmosphere. But atmosphere, you can see here, there are so many wavelengths which are absorbed by atmosphere. So if I am making a measurement from the space, there are the blue here in the, what you are seeing are called atmospheric window. So you can make measurement only in the atmospheric window, because once, even if the Earth is radiating or sun energy is coming, it may, some of energy may reach, but atmosphere will attenuate while sun rays come through the atmosphere on the ground and when reflect, so most of the energy will be absorbed. So you have to make measurement, you have to remember, only in atmospheric windows. That is why you will see only our all instruments take care of this and they make measurement at particular wavelengths only. Except that sometimes I want to make a measurement of say water vapor. Here you can see water vapor somewhere around 5 micron. Water vapor here. Water vapor is absorbing a lot here, 5-6 micron. What I can do is that I want to find out the content, how much water vapor is there. So I know how much illumination from the sun is coming. And finally, when I get back atmosphere or 300 kilometers, because Earth is at 300 Kelvin, I know what is the radiance I should get and how much I am getting because in that wavelength. That will tell me how much it is absorbed in the atmosphere. And from that absorption, I can find out how much water vapor is there in that column through which the radiance is coming. So sometimes you can even use that information. Sometimes you use that information in a different way, in the sense that I am making measurement which are windows, but still to some extent water vapor is affecting. So I'll make one measurement of the water vapor in water vapor band. Then I will find out how much attenuation, and I will add that attenuation to that my measurement, so that I know that this is what I should be getting in the absence of water vapor. So this type of measurement, this is what we call remote sensing. Now the question is, how do I differentiate whether it is say wet soil, whether it is dry soil, whether it is vegetation? So if I draw wavelength or color versus the reflectance, every target on the earth will have a certain signature. This is called signature. How it will vary with how its reflectance varies with wavelength. That is called spectral signature of that particular target. Now, what I am measuring is radiance, but I can find out reflectance because I know how much sun is illuminating it and how much atmospheric absorption is there. So I can, suppose I am seeing in the window, there is no atmospheric absorption. And sun's temperature we know at 5700 Kelvin or 5800. So I know how much illumination was there at that wavelength from black body radiation, Planck's curve, and how much I am getting. So I can find out what is the reflectance. Now, suppose at this, so my reflectance, suppose I have again 3 equation and 3 unknown. Suppose 3 unknown. Again, I can solve the equation and find out how much is dry soil there, whether the soil is dry soil there, whether it is a wet soil or whether it is a vegetation. So it is only from spectral signatures that you can find out the characteristics of the targets that are there on the earth. You are measuring only radiation, and from the radiation measurement, you are deriving various parameters of the targets. Now we have 2 types of remote sensing sensors. One are passive sensors. Passive sensors means what? Either camera, radiometer, human eye, means somebody else is illuminating that target. In case of say sun or say earth is radiating. So the source is not with you. Source is somewhere else. And you are that source, whatever illumination it is doing, reflected or emitted energy you are seeing. So those are called passive sensors. While active sensors, what you do is that you don't depend on external source. You carry the source on the satellites, like radar, sonar, laser. So you illuminate with laser, you illuminate with radar, radio frequency, or you in our measurement sonar, many times you illuminate with sound waves, and those sound waves are reflected and you measure the scattering or reflectance. So those are called active sensors. So say simple thing is that whether we take a camera with flash or without flash. When it is with no flash, then it is a passive sensor camera. When you are using a flash, it is an active sensor. Now this I will not go into the details because I have told you all the things. Now in what way we do imaging? We can do imaging in basically 3 ways. One is called frame, area. I put a camera like what we use our cameras in our mobiles or earlier we used to have our digital camera. You take a snapshot, and that snapshot is taken simultaneously of the entire square or rectangle, whatever you want to design. That is called field of view. So Bhaskara TV was like that, where we were taking snapshots of 300 kilometer by 300 kilometer. You take one snapshot, let the satellite move. Before it moves 300 kilometers, take another quickly, because you don't want to have a longer exposure. Otherwise, satellite is moving, so there will be a smear. So you take very fast those things and then wait till you reach you know when it will reach, how much it has moved, because the satellite motion linear velocity is fixed at a particular height. So you take snapshots. So that is called frame cameras or area staring. You are doing staring. Other thing is what, at any given time you are seeing one or couple of pixels only, picture elements, and then you are scanning. And when satellite moves in other direction, it has moved, take another strip. So strip by strip, actually one pixel, before satellite moves, total one pixel, you cover one strip, go to the next strip, again next strip you cover. So this is what we are doing. These are called optomechanical scanner. And our VHRR or inset series, whatever I told you, that we have very high resolution radiometer which takes the picture of the earth every half an hour. So it is this type of sensor, but their satellite is not moving, so we have to move mirror in two directions. Take one picture in this direction, say east-west direction, move the mirror little north, south, and slightly in the north or south, depending on how you are taking a picture. Take another strip, so pixel by pixel and strip by strip you cover, but you are doing very fast. One strip of about 8 kilometer or 9 kilometer, you are covering all one end of the earth to another end of the earth. You are covering, and that too at equator, you are covering in about 1 second. So you can take those pictures very fast, and then you can generate, take this data, send this data and generate. Now there are reasons why you do that. Other is that what we call is that line scale camera. So you have large number of sensors, and they are all our remote sensing satellites are this type. This is our weather satellite. This is our remote sensing satellite, which have a linear array. So in one direction, across the motion of the satellite, that suppose satellite is, as I told you, that all our remote sensing satellites are going either north to south or south to north. Means they are going both way, but we can take picture in one direction, other is night. So of course, if we have IR, we can take those pictures. But if we have only visible sensor, we can take picture only one time. So suppose I am going from daytime is from south to north. So I take strip by strip, image one strip, and then send that data. When satellite moves by one strip, then I take another strip and go on sending that data. So I have large number of detectors in the cross-track direction, or what we call swath, that is across the motion of the satellite, 90 degree to the motion of the satellite. So you cover those strip by strip, and that's those strips, because you have large number of satellite, you get advantage of signal to noise ratio. So all of our satellites, which are their remote sensing satellite, we are using this, because then our efficiency is good, coverage efficiency is good, we get signal to noise ratio. But here, because you do not have that time constraint, you see, here you do not have time constraint is in your hand. Here time constraint for low Earth orbit, satellite is moving, while in geostationary orbit, satellite is fixed. You can decide when your mirror move. Only penalty which you will get is that to cover the entire Earth, you will take longer. So you can afford to do that, and you have to calibrate fewer number of sensors. Your life becomes easier, particularly for infrared wavelength. Here in IRS, so far we have not or inset this low Earth orbit series in Indian remote sensing satellite. We have not used IR sensors, and we have not used IR sensor, so we can afford. But now even IR sensors in strip mode have become available, and probably we may use these sensors. But here, because that constraint is not there, that you have to cover this area this much fast, otherwise you have to scan very fast, because satellite will move away and you can't afford to do that. Of course, Landsat was doing that, but then there are other limitations. Your signal to noise ratio you have to increase by some other means, because your integration time for the signal is very low. Some of you would have heard the name of LoRa, that is long range oblique photography. Suppose I am at the border, I am flying along the border, and I want to see the area beyond border. Then I don't look straight down here, but I am looking sideways. I am looking beyond my border. And that type of thing I am doing, that is long range oblique photography. I am looking oblique. So some of the sensors which are there on aircraft mounted, and when I want to do reconnaissance, I do use this type of sensor. Of course, our radar set, which is radar set 1A, which will be launched tomorrow, it also looks oblique, but it doesn't look oblique that much. But it also, for proper operation, it has to. It is not looking oblique for this reason which I am telling, that you can't go into somebody's border and take their pictures. We have to take within. We have to remain within our border and take the pictures for reconnaissance purpose from somewhere. So that we are doing from aircraft. I was so near, at least we don't use that. ISRO doesn't use that, but they are being used. That is called LOROP. But our radar set, which is to be launched by tomorrow morning, I think less than 12 hours by now, unless they have changed the schedule. I have not read recently. So it will be launched, and that also looks slightly slant, but that slant looking is for some other purpose, because it is a radar satellite, or it is what they call SAR. We will look into it, if time permits, we'll look into that, but this is what we are doing. Now, what are the types of resolution? So suppose I want to look fine detail, then I will call it a spatial detail. Suppose I want to look at, say, half a meter, 0.25 meter, 1 meter, 10 meter, 10 meter, 12 meter, or angular resolution. When it will be for sensor, it will be better to say 1 microradian, 0.5 microradian, 10 microradian, 50 microradian, 100 microradian. So if I look at finer detail, that microradian also have to be smaller, and on the ground strip, because that ground strip will be nothing but microradian multiplied by the arm length, that is height of the satellite or radius of the satellite, from, say, satellite height to the surface of the earth where it is looking, range. So range multiplied by your angular resolution will give you ground resolution. So that will call spatial resolution. And spectral resolution, how many colors I am looking, very narrow color I am looking, or white color bands are okay for me. So that is called spectral resolution. Then radiometric, how small change, means, because if I want to see a very small, my signal may be, say, 1 volt, but I want to see 1 millivolt or 1 microvolt change on that 1 volt signal. Do you think I can see or not? That will depend on the noise of the signal, how much noise it is there. So that is called radiometric resolution. So my radiometric resolution, and last one is temporal resolution, means how frequently I'll be able to come to. So these are the resolution which you define for remote sensing satellites. Now, I was telling you that our VHRR, or our insert 3D sensor, say visible sensor, has a resolution of 1 kilometer, but still we are calling it high resolution imager. And for our remote sensing satellites, say Cartosat 2 also is more or less 1. Of course, its resolution is better. Its resolution is better than 1 meter. But angular resolution difference, you see, it is only 50 times of thing. Say, not a 50, even 25 times. Say, my angular resolution of INSET 3D visible is about 25 microradian, while my angular resolution of Cartosat 2 is about 1 microradian. So angular resolution is only 25 times. But you see now what happens. When I am looking on the ground, okay, one is at 36,000 kilometers, other is at 500 kilometers or 600 kilometers. So one at 500 kilometers, 1 micron will give 0.5 meter resolution. But when I take it to 30,000, my resolution for 25 micron, I will have a resolution of 1 kilometer. So when I go up, more up, here it shows for the same microradian resolution on the ground, when I am seeing I am farther away from the ground, my resolution deteriorates very fast. So that we should understand, that even if we are calling it very high resolution radiometer VHRR, its resolution, angular resolution is higher, not the resolution on the ground. Say for our Cartosat, you may have Cartosat 2, it is 1 meter, slightly less than 1 meter. If you have Cartosat 3, it is 0.25 meter. But they are all at lower level. Of course, their angular resolution may be 20-25 times better. But the data which I am getting from insert 3D imager, or earlier Kalpana, VHR are very high resolution radiometer. They were earlier were 2 kilometer in Kalpana and 1 kilometer resolution in visible from. Only thing is that because you are very far, you want to see cover larger area very fast, because for atmosphere, say you don't want to, for atmospheric study, I don't think you need 1 meter or 0.5 meter resolution, particularly the type of atmosphere which we want to understand the atmospheric and put it in atmospheric model. So these are good enough. That is what we were told by IMD, and that is what we are using. Now you can see spatial resolution. As the spatial resolution, how you see the same ground. Suppose you are seeing at 0.5 meter by 5, the details that you can see, and 20, say 10 meter by 10 meter or 5 meter, you are not able to see those details. So spatial resolution tells you what details you will see. Here you can see 30 meter resolution, and the same area, if you see here, this red area here, you can see how clearly, and this area at 30 meter you cannot see. Similarly, radiometric resolution, as I told you, is sensitivity. Now, sensitivity means finally what I will do is that if I do not have a good signal to noise ratio, I will not have a large number of bits. I will send the data in 2 bit or 3 bit or 4 bit. So if I send the data in 2 bit, you can see how it will look, and send the data in 8 bit. So radiometric resolution, you can see the difference, the details that I can see. Similarly, temporal resolution. So these are the various resolutions which we talk. We talk in general the basics of remote sensing. Now we will go to imaging missions of India, but we will take some break small, because 1.5 hours, less than one. We started about 6:15. I have talked for an hour. We can have a break for 5-10 minutes. Hello? Hello, somebody there?
Yes, sir. Yes.
Can we have 5 minutes break?
Yes, sir. Sure, sure.
Shall I stop sharing?
Yes, sir. That can work out.
Let me see how to do that. To do that, stop sharing.
Sir, you have to go to the Google Meet window, and there you can click switch off. Google Meet, sir. Google Meet.
Okay.
Yeah, stop sharing. Okay, so students, we are having a 5 minutes break over here. So as the question answer poll has been opened, so please you can ask your questions here. Yes.
What I thought was that basics I will cover a little more detail, because as I understand, all students are from college and they have science background. So if we understand the basics of remote sensing, other is what type of satellites or what type of spacecraft, that is our planet, say Chandrayaan 1, Chandrayaan 2 or Mars, that we will cover a little faster. So we will go to that first, and what all we have done in when we started our Bhaskara 1, that was the first remote sensing satellite we can talk, to all the way to Cartosat 2, Cartosat 3. So that we will see how much we have covered, but that we will cover a little faster.
Yes, sure. Yes, Akanksha, please.
Yeah, okay. So if any one of you have any questions, you can ask them.
Hello, sir. I have one question. May
Yes.
I?
Yes.
Sir, I didn't get a basic difference between LEO orbit and Geo, like satellite.
Okay. See, LEO is low Earth orbit satellites. Are you able to hear me?
Yes, sir.
Low Earth orbit means they are orbiting around the Earth in an orbit which is about 500 to 1000 kilometer from the surface of the Earth. So it is low Earth orbit. The orbit is, say, maximum you are 500 kilometer circle, or you are 1000 kilometer circle. But you are going, because you want to cover the entire Earth, you are going from pole to pole. So it is a polar orbit. It is sun-synchronous orbit in the sense that you are taking picture at any given latitude. Particularly, we always talk in the terms of equator. At equator crossing time, say 10:30. Every time when it crosses the equator, at that time, at that location, local time is 10:30. So we are using that type of low Earth orbit for remote sensing. Well, geosynchronous orbit is at 35,000 kilometers. Now, what happens when you are at low Earth orbit? Your satellite makes one round of Earth in about 100 minutes. You are going very fast. So, satellite with respect to Earth, if you see, satellite is moving. We saw yesterday. I don't know whether it was seen from Pune also. We saw International Space Station. If you anytime you see it is moving very fast, you can see but within 5 minutes, 10 minutes, it will go from one end to other end. So it is moving very fast with respect to Earth. So you have to take pictures very fast. But there are some advantages, as I told you, which we discussed earlier. So all our remote sensing satellites are in low Earth orbit satellites. While for communication, your requirement is different. See, my requirement is that my satellite should not appear to be moving with respect. It should appear stationary. And for appearing to be stationary, the angular velocity of the satellite should be same as that of the Earth. That is about 1 degree per. Not that one. In 24 hours, you are going 360 degrees. In 24 hours. So that type of orbit you have to have. In 24 hours, you have to go around the Earth once. Of course, velocity of the Earth, linear velocity if you consider at equator, because satellite is at equator. Linear velocity of the Earth's surface at equator is about 450, 460 meters per second. While the linear velocity of that satellite is about 3 kilometers per second. So linear velocities are different, but angular velocities are same because Earth's radius is about 6,300, 6,400 kilometers. So linear velocity divided by the the length of the RE, radius of the Earth, and the linear velocity of the satellite divided by the height of the that is 35. They both will give angular velocity. So angular velocities are same. Same angular velocity means that satellite will appear stationary to us. Stationary means now when satellite, I can put my antenna at a game because it is used for communication. It is not either communication or for weather. For weather also, I don't want it. I want to take the same picture of the same location as far as I am concerned. I want to see the weather of 1/3 because there are other people have put their own satellite there. So I want to see the weather over 1/3 of the globe centered over India. So for those type of satellites, we use geosynchronous or geostationary orbit. Geosynchronous and geostationary orbit, little bit difference is there, but I was not making difference because geosynchronous means with respect to time. Orbit takes 24 hours to complete, but it can have some inclination with respect to equator. But geostationary means, and then it will appear to be making a figure on the equator, figure of 8 over a whole day. And the figure of 8 will go up and down by the amount to which it is inclined with respect to the equator. But if it is exactly on the equator, it will appear completely stationary, and that is why it is called geostationary orbit. Did I make it clear?
Yes, sir. Yeah, got it. Thank you, sir.
Yes, sir. There is one question in the question answer section that what kind of image technology is used in James Webb Space Telescope?
Oh, it's a big question. That is an astronomy satellite. You are not looking at Earth. You are looking at galaxies, stars which are developing, stars which are being made. You are looking much more farther. How much farther, I will tell you. Suppose we are saying that our universe was with a big bang. Universe came into existence 13.8 billion years ago. So light which is coming from say 13.4 or 13.5, 13.6 billion years ago, I want to see that light, the beginning when the Big Bang occurred, just 400, 500 million or 300 million 300 million years after the Big Bang. I want to see what happened at that time. I do not have the data. So we are seeing that type of radiation using James Webb Space Telescope. It is a very big, there can be a lecture of 2 hours. If you are interested, we can have that lecture, but we cannot cover within 5 or 10 minutes.
Okay, sir. Yeah. So I guess that the answer would have been answered. So next question is, how do we classify a launch mission as a partial failure versus partial success?
Okay. partial failure or partial success are same, more or less. Okay. If I want to be positive, of course, at this time being positive is not good. So if I want to be positive, what I will say is it is partial success. If I want to be negative, I'll say it is a partial failure. Now, when I am deciding to launch a satellite, I have been told I have told the launcher guy that I want to put my satellite at this location. I tell even the location at which I want to have. At this location, at this height, and with this much initial injection velocity. So location, that means longitude and latitude. Then I will tell longitude, latitude. Above, of course, it is at this height, say 500 kilometers, 700 kilometers, and what tangential velocity. I tell the launcher to do that. Now, suppose my launcher does a good work reasonably. It puts a satellite which will be in an orbit, but not in a desired orbit or in the orbit which I have asked. It puts either say my location where he has put is not correct, or inclination, I have told inclination is not correct, or my satellite, I have told him to put say in an orbit where say farthest point is Geo Orbit, as I call it. Farthest point is 30. He is not able to get 35,000, but he gets 30,000. So it is not an orbit which is agreed upon, but still I can use some of the fuel of my satellite. Most of the time, and at the cost of the satellite life, I'll be able to use either that satellite as it is with certain limitations, or I'll be able to correct using my fuel at the cost of life. That is called partial success for the launcher. Did I make it clear?
Yes, sir. Yes. So I hope that question would have been answered. So next question from Vyavare Parth is, when any satellite get destroyed, then the parts of it are moving in space with the speed of bullet. So without destroying other satellite, how like other ISRO as well as other space agencies handle such situation? Like I would make it much clarified that how is space debris managed?
See, first thing what we have to see is that we are not driving, satellites are not like driving a vehicle either in say Pune or Bangalore or Ahmedabad. FSR, the way you cut somebody, you go from left, you go from right, you come from behind all of a sudden, and even somebody is turning left, you go straight from the left. Satellites don't do that. Their orbits are very precise. Even if they break, they're 10 or 15 pieces. Initially, you will not know in what orbit they are, where they are. But if you observe them for a long time, say, and there is somebody who is observing, so they know how many pieces are there, those pieces are in which orbit, and then what you can do is that because they are always, so you will precisely know when that piece will be where at what location. And that happens in our launcher also. When we are launching a satellite, we study that our path of launcher, is there any satellite or any, not only satellite, any part of the earlier launcher which either we have launched or other will be on its path, or debris will be on its path, even a small debris, and then either we delay the launch or we change the location, or we change in a slightly different orbit, so that on the path you will not meet with the debris. That is one thing. Second thing what we do is that whenever there is a requirement, particularly in the geostationary orbit, we did very recently to one of our satellites, that is I think INSET 4. What we did is that those satellites, that orbit is a simple ring, while here if you see lower Earth orbit, it is a sphere. It is a sphere, while there geostationary orbit is a ring. So you can put only so many satellites. So when our INSET 4 satellite had completed its life, there is a requirement by the international authority to shift it up, because shifting low is very expensive, and you will pass through lot of, because 36,000 kilometers down, but you send it up by about 340 kilometers, we sent it up. So it will not, now that satellite, and then you observe radio silence. Whatever satellite was transmitting, stop transmitting. You give a command, there are always commands, you can make it stop transmitting anything. Now, so you can send a command to it, but it will be, oh मूंगा हो गया, कुछ नहीं बोल सकेगा, वो कुछ नहीं करे. तो दूसरा ये है, आप करो उसको ग्रेवयार्ड ऑर्बिट में भेज दो, या तीसरा लोअर अर्थ ऑर्बिट में है, तो आप क्या करो, उसका फ्यूल बर्न करके नीचे लाओ, नीचे लाके आप क्या करोगे, ब्रिंग इट टू अबाउट 150-200 किलोमीटर, एटमॉस्फेरिक ड्रैग से वो बर्न हो जाएगा. सब लोग ये करते नहीं है, बट इवेंचुअली व्हेन लार्ज नंबर ऑफ सैटेलाइट you will have to observe some discipline. There are certain things which you will have to do. Those satellites which do not have a facility, what they are doing is that they are making some either net they are making so that defunct satellite can be caught in the net and they can be brought down in the net, or by pushed by the gravitational force, bring it down, and then they will enter the atmosphere and they will burn. So various methods are being thought, but there is, except sending the geostationary orbit satellite in the graveyard orbit, that is orbit about 300 to 350 kilometers above the geostationary orbit, no other things are proven and established. They are trying to do that. Eventually they will have to do.
Yeah, I hope that it was very explanatory answer, so that clears everyone thought of how the satellites debris is being managed. So next question from Kavane Sandesh is, what if we exceed the limit of 36,000 kilometers orbit? Wouldn't it provide a large FOV?
A large FOV means it's not good, because if it is not large FOV, means it will provide a large, suppose my sensor has a resolution of say 1 microradian. Sensors have resolution always in microradian or degrees. So I have 1 microradian. Why I am telling multiplication easy. I am at 500 kilometer. I'll be seeing 0.5 meter on the ground. If I am at 1000 kilometer, I'll be seeing 1 meter. My 1 picture element will be 1 meter. If I am at 10,000, I'll be seeing, or say 10,000, I'll be seeing 10 meter. So larger means I am seeing less and less detail, but larger areas. I don't want to do that. So it is not that you will deliberately do it. Only when there is a partial failure, as I told you, they may go. So either you live with a poorer resolution. I will call it poorer rather than larger, because you are not able to see the details. So it is that way the picture is poor. So poorer resolution, you live with it, or you change your satellite orbit, bring it to a level using the satellite fuel and at the cost of life.
Yeah. So next, Bhakti Bhatt is asking, what does it mean
So
when they say we
take
have
one
to take
picture.
the
We will take one question, and then we will start our lecture, because that is also long. And
Yes, sir, sure, sure. Sure, sir, sure.
Yes.
So,
Yes. Last question.
Bhakti Bhatt is asking, what does it mean when you say that we have to take the images quickly? Can't we program the satellite so that it takes the images on its that will increase the efficiency?
Quickly means it is all programmed. You have to program it quickly. Let us see. Let us say that satellite is moving. See, ground trace of the satellite, not satellite. Satellite is moving little. Say 500 kilometer satellite will be moving at about 7.6 kilometer per second. But you project it on the ground satellite. So ground is nearer. Now 500 kilometer less than 64,000 kilometers. So my ground trace is moving slower. It is about 7 kilometers per second. Now suppose I want to take a 7 meter. My resolution is 7 meters. So what I have to do is that before satellite moves 7 meter, I'm talking 7 meter because it is easier. It is about in 1 millisecond. I have to take the picture. My exposure time cannot be more than 1 millisecond. Because if it is more than 1 millisecond, what will happen is that my satellite on the ground or ground trace of the satellite will move more than, so I will have a smear. So that way, lower the resolution. I have to program my satellite to take picture faster. That is what I am telling quickly. What I meant quickly, it is not that you are doing it. You have designed and you have put it in the you have put in the electronics that you take it. You put some latitude, because something happens. Suppose instead of 550 kilometer it goes. So you give some latitude change, so that. But then you have to take the picture. We will see how fast we have to take the picture to avoid smearing. Anytime you have a camera and I am taking a picture, my hand moves, I will get a blurred image. So I don't want to take a blur image. So depending on my resolution and the motion, I have to take picture at a particular rate. Quick. My exposure time will be very fast. So I take exposure time. Then I may wait also, because I will close the shutter. I wait for some time because I have not covered, and then I can get sharper pictures.
Yes, so I hope all the questions which have been asked till now has been clearly answered. So now we will continue with our session now, and if time allows, we will take the question and answer session in the end. So
Okay.
yes, sir. Over to you, sir.
Are you able to see?
Yes, sir. We can see the screen now.
Okay. So now we will see the imaging missions. We started, uh, uh, if you see here, we started in about 75, 76 time frame. And in 79, we launched Bhaskara. That was an experimental satellite. It was at about 500 kilometer. We will see exact 500 kilometer at 50 inclination of 50 kilometer, orbit inclination of 50 kilometer, and it was taking it had a snapshot, first type of camera, like our standard mobile camera. It was taking picture with a resolution of 1 kilometer. So we started at that time. It was then RSD1. Then we went to Indian remote sensing satellites. So first we started using for Indian remote sensing satellite IRS1. I will not tell every time Indian remote sensing. I will call IRS1, IRS2. They had linear imaging sensors. So that was it itself tells it was a line sensor, and because satellite moves, you can take data line by line. So that is what we do. Now here we have launched the satellite for different purpose. Say one is land and water. So earth of what is it that you are observing here? So our resource set, then our say even GI set, of course it was not successful. Various even our RI set. RI set is used both for land and water purpose as well as for cartography. So which we are going to then IMS. These are for land and water. Then we have cartography. What is the requirement of cartography? You don't want to take the data in multiple bands. You don't want to in different colors, because there we saw that every target has a spectral signature, and if I want to recognize the target or find out the characteristics of the target, I have to take in multiple color or multiple wavelength. While in cartography type of thing, I want a black and white image. I can differentiate a building. I don't want to see the color of the building. I want to see which building is, which road is located, how the roads are going, how total they call urban sprawl, how villages are being converted to urban areas. So those with time how they are changing. So I want higher resolution. But I saw say our TES was, that is Technology Experiment Satellite 2001, then Cartosat 1, Cartosat 2A 2B, then RISat which we launched last time and now we are again launching, then Cartosat 2 CD, Cartosat 3, then these two are RISat 1R and RISat 3 are yet to be launched. But these are the satellites which are already operating for cartography. Then we have satellites for atmosphere and ocean. There you don't want very high resolution, but you need multiple bands there. Poorer resolution, but multiple bands. So we have Kalpana, Inset 3A, Inset 3D, Inset 3DR, GI set, of course, as I told you, that was not successful. Then Saral, Ocean set for Ocean set 1, Ocean set 2. All these were either for ocean or for atmosphere. So ISRO has launched satellite for different purposes. Otherwise, you will think why we are launching. Because each satellite which we are launching will serve a particular purpose. Then you will think why we don't launch satellite. Well, all purposes will be served by a single satellite. Either that satellite will, and then we will start doing compromises. We will cut corners. So if we have specific custom-made satellite for a custom-made application, one thing is that we can make them very efficient, and secondly, they will not be very large, and thirdly, and more importantly, there is a redundancy. If one satellite fails, all your payloads don't fail. One of the payload will fail. And then fourth thing is that as the technology develops, we can only change the satellite, which suppose for cartography, my when I started for cartography, I was seeing, say, even Cartosat 1, that was cartography. It had a resolution of 2.1 meter, of course stereo imaging, but 2.5 meter. Now I went to, I know that 2.5 meter was good enough at that time, but now people are giving you imagery of 0.25, 25 centimeter from imagery, or even 50 centimeter. So I have to change my technology. So if Cartosat is there, I don't have to change all other things which are there on the thing, or again put the same things on Cartosat and do it. So I custom made satellites we are launching for a particular purpose. Here, if you can see that how the development of ISRO satellite started. On June 7, 79, we launched Bhaskara 1, which had a resolution of 1 kilometer. You can see how from 1 kilometer distance how the picture looks. And on January 10, 2007, after that we have launched, but I had this data, so I used this data. Cartosat 2 we launched. Then we have launched Cartosat 2 series, 2A, 2B, 2C. 2C, 2D were slightly better than this. Then 3A, where we have a resolution of half a meter. But you can see the type of details we can see. So that is how ISRO has progressed. 73, say 360 meter, then 188 meter, 73 meter. That is how the technology developed, how the requirements changed, and how we started seeing. Now, Irs pan is panchromatic camera. So that is what I told you, that camera which takes picture black and panchromatic is nothing but black and white picture. I am taking black and white pictures. Just 1 minute. Are you able to see?
Yes, sir. Yes.
There was a slight drop somewhere. I don't know why. So you see, I have Cartosat. Now this earlier, so in the beginning, Cartosat, what I call IRS pan. I had a resolution of 5.8 meter. Then I went to TES. TES I had launched quite early, 2001, 2002 time frame. But that had a resolution of 1 meter. But that had certain limitations. You will see what were the limitations. Then I said a very good satellite, Cartosat 2, Cartosat 1 and Cartosat 2. Cartosat 2 had a resolution of 2.5 meter. You will think that we have launched a TES with a resolution of 1 meter. Why we are launching Cartosat 2, Cartosat 1 with a resolution of 5 meter? You see, here you can see the 3D, because it has two cameras and they are properly faced. One is looking in the front, other like our eyes. One is looking left, other is looking right. So one is looking in the front, other is looking behind. So from these two views, you can generate 3D imagery. So it was used for generating 3D imagery simultaneously. Then less than 1 meter, we use Cartosat 2, 0.8 meter, 0.5 meter. Of course, we were using a different technique for that. Here, some of the ocean and weather satellites will not go deeper into that right now, because I have told you all the resolutions and details. And here, how the cameras look, how the Cartosat camera, it is not the full satellite. These are the cameras or payloads, what we call. Camera is, when you put on a satellite, you call it a payload. We are not talking of the total satellite, because satellite has bus systems. Those bus systems are supportive systems. Like these cameras need power. They have to be maintained at a certain temperature. Then we have to give a command. So you need telecommand. Then they generate data. So we have to receive the data. Then we have to receive not only the imaging data, but their health data, whether the temperature has gone bad, whether the voltage where we want to, so that we can do the analysis on the ground. So all those bus systems then control the satellite, so that cameras are always looking at the correct location where, so control system is there. Then so many other support systems are there. We are not talking, and those support systems are called satellite bus systems. We are not talking today of those bus systems. We are talking of the payload. So these are, and payloads for remote sensing are different type of camera. So you can see here different cameras. How these are real pictures of the cameras. How they look. They are real. When they were made in, all the cameras, what you are seeing, were made at Space Application Center in Ahmedabad. And those cameras, how, when they were being made, some of them when they were being made or when they were ready. Maybe first model, so it may not look as good because we make couple of models. So you have taken, some of these pictures are of the early models, which we have not launched, but we have kept on the ground for studies. So, but they are fully representative. So these are the types of different cameras which we have made. These are not the, these are 3D. This is drawn by picture, 3D pictures, 3D studio or whatever. Okay, so that you can have a cut view or a cut cross section at different location, and you can find out how from inside they look, so that here you can see them. Now I was talking of Bhaskara 1, which was launched on 7th June 79 and Bhaskara 2 on 20th November 81. You can see here it had a 50-degree inclination. It was on a 535 kilometer. It was using very small 47 watt power. Its weight was 440 and it was a spinner, means it was spinning. Now you will think that when it is spinning, how can take a picture? That is what when it is spinning, you have to generate that. These are the camera here. See this type. This is camera here on the belly, and this portion, this top to bottom is oriented in such a way that you are seeing the belly continuously, moving belly of the satellite. This is the belly. So when that belly, the portion on the belly where the camera is there, when it is looking at the ground, there is a way to detect that camera is looking at the ground. So when it is moving 7 to 10 RPM, revolution per minute. So when camera is directly looking, you expose it for, because it is moving. So you have to expose for 2 millisecond, 1 millisecond, 1.5 millisecond of that order. Take a picture, and for then the camera will go away. So you have the remaining time available for sending the picture, because we could not at that time send the data very fast. Our telemetry was not very fast. So for sending that data, we take a picture, wait for some time, and then before the that 300 kilometer by 300 kilometer, that our 340 by 340 kilometer, that thing, our picture is over, you take another picture. Now this was a satellite which was our first communication satellite. I am not talking of communication satellite, but this was launched by Ariane, that we got a pre-ride. So within one and a half year, we made one communication satellite with one transponder. You will be hearing of it later, but I thought because this was our first satellite and how we designed, it is a very interesting history, which probably you will see tomorrow, the day after tomorrow, or whenever that communication satellite towers in the sky, whatever towers on the earth, whatever that is there, you will see. So we'll not discuss that, but this is IRS-1. When we started IRS-1, you can see that these are the IRS cameras. 2 cameras were there, but here you see 3 cameras. One is in the center and 2 are on the side. The 2 on the side have a higher resolution. So when you have higher resolution, what happens is that because you are using the same strip of the sensor, then it will cover a smaller swath. So if I put 2, suppose this has a resolution of 70 meter, well, this is a resolution of say 35 meter. So if I put 2, then 2 together will give the same area as 1. So 2 high resolution camera and 1 low resolution camera. You can see here that is list 1 is a smaller resolution, 70 meter resolution camera, and list 2 is a 35 meter resolution camera, approximate number. And they have 4 spectral bands. I told you that because these are for agriculture type of thing, you have to see in multiple band. You see in multiple band, and at a time swath, because swath will determine how fast you will be able to. I can put much larger swath, but then complexity will increase. So I am seeing a strip of 150 kilometer wide long swath or strip across the path of the satellite. So 148 kilometer, and the next pass or third pass, I'll see another 148, and that way I will cover the entire. That is why it takes time. And my data rate, even with that, data rate was 5.2 megabits, because you are generating large data. And for list 1, for list 2, it is double the data rate, because you are double the number of, you have only half the time. You remember that because you have 36 meter, satellite has to move only 36 meter, and you have to take another picture. So time available for the satellite to move 36 kilometer is much less, half the time which is available for 72 meter. So double the rate and 2 camera. So total rate is 4 times. You see how if I make the resolution half, my data rate becomes 4 times. So that is what is why limitation comes many times, that your data rate is not, you cannot handle that, your telemetry, your transponder cannot handle that data rate at that time on that satellite. So you have to do certain tricks. We will see what tricks we were doing. Then we had IRS-1D. These were the initial IRS-1. In between, there were many. I am not going to all of them. Here, you see, there are 3 cameras, list 3, which had a resolution of 23 meter. Now you have gone from 35 meter, now 23 meter. Then you had a panchromatic camera. Here, this is a panchromatic camera, which has a resolution of 5.8 meter. Panchromatic means no color. Here, we had 4 colors, plus 1 color in short wave infrared, and short wave infrared means your eye cannot see. Even 0.86 your eye cannot see. So here that is called near infrared, and this is short wave. So you are seeing in multiple band for the purpose for which they were put. Similarly for VIPs, in VIPs what we are doing is that wide field sensor. Wide field means you see, you are seeing 804 kilometers, but at a coarser resolution. Now what happens? Let us see. Now I will show you. Okay, a little bit later I will show you that you have 3 cameras. That is nesting. One camera sees much larger strip, but then its resolution is poor. Other camera sees with 23 meter resolution, but its strip is smaller. Then third camera is a panchromatic camera where you have strip large but only one color. So different, as I told you, sometimes you put, you know that it is not a problem. So suppose for cartography type of work, it was not a very good cartography work. I can do it. I can see as a large forest type of mapping I want to do, where details I am not interested much, or barren areas I want to see. I can use VIPs. And when I want to see agricultural land or agriculture crops, then I can use list 3. So these are the type of, that is what called nesting we do. Now after that we had a TES. This is the TES, that is Technology Experiment Satellite. This satellite we put in about 2001, 2002 time frame. Yes, October 2020, October 22, 2001. Now, why we made this satellite? This satellite was, we needed a very high resolution, better than 1 meter. We did not have many capabilities at that time. But this, you remember, was immediately after Kargil war. Nobody will give you satellite, or nobody give you, if you want to study around the border areas, what is happening, whether there is some problem or not. Our border we want to secure. So for that purpose it was made. It had a nadir, means look down from a 560 kilometer orbit, you are looking at 1 meter. Now because we could not make integration time or exposure time very short. So we were doing some technique which is called step and stair technique. What you do is that you reduce what you do is that satellite is moving, but you can go on changing its orientation such a way that the line of sight is not moving that fast. Line of sight is moving slower than the satellite motion. So what will happen is that you will be able to concentrate on a given area a little longer, so that you can collect signal for a larger time without smearing. At the same time, your exposure time is larger, so your signal to noise ratio is better. And that is called step and stair imaging. So we did step and stair imaging. Then because we are doing this step and stair, we are moving the satellite, so sometimes your antenna may not point. So we have a movable antenna there, so that you don't have to move that antenna very fast when you may have to move. Anyhow, for all low Earth orbit satellites, you have to move your antenna. But otherwise what will happen is that your antenna will, even if you move your antenna, that antenna has gone somewhere else on the satellite. It will never point to our antenna. So you try to point it to the antenna. So we had that X-band phase array antenna, so that you can change the beam direction. So beam direction we were changing. We had solid state recorder. So even if the satellite is not on Indian region, you take the data, store the data in the tape recorder, and then they are solid state tape recorder. They don't go bad. Basically it is a solid state memory. And then when the satellite comes over the Indian region, you download that. And for that, whatever here, what you see in green color is how it was achieved using the bus systems. I will not go into the bus system, but you see now, up to now, what we were using is that our camera aperture, or the first element, primary mirror, aperture was very small. Now here is the first time that we have an aperture of more than half a meter. And f7 means f7 tells you see speed, particularly it is called speed. So it was little slower, but most of the cameras are slower because you want to see the depth. When your camera is f7, your depth is better. So you can see it here, and we had done the velocity reduction. Suppose we were not changing the satellite orientation during the in the direction of the satellite motion. If we were not reducing the line of sight velocity with respect to satellite velocity, we will need an integration time or exposure time of 143 microseconds. But what happens is that because we are moving, we can make that integration time or exposure time 883 microseconds. So that 6 times larger exposure time we can get, so that our signal to noise ratio is better. But as you can see here, you see satellite is here, we are looking slightly in ahead, then you are looking here, and satellite you are looking back. So I have covered only this much area, while my satellite has moved this much. So I should be seeing, neither if I am seeing here. So again, when I here, I'll make my camera look ahead. So there will be some gaps, but whatever area I am seeing those areas in this by this step and stair method, which have much higher radiometric resolution. That means signal to noise ratio. Because now there are two advantages because of that. I have to run my electronics at a slower rate. I don't have to run, and my data rate also is not that large. I can handle, my transmitters can handle that data rate, because my data rate is generated at the non-velocity. So I can have a lower data rate because I have increased my integration time. I have to take one integration time, whatever data I have generated, I have to send that data on integration time. So I have increased my integration time 143 microsecond to 883 microsecond. So 6 times larger. So I have time to send the same data 6 times larger time. So my launcher, my transmitter can handle that. Now you can see the type of imagery that would go, the resolutions which we go. I'm not going into the application, so we'll not see. Now this was Cartosat, this was our TES. We made this TES. There were some limitations. It was very heavy. We had used Invar, which is as heavy as steel. So we wanted to continue with do the improvement on that. But before that, we went to Irs Resource Set 1. Here, as I told you, that nesting, which I was talking of earlier in Set 1D. Here, there is a nesting you can see. I am seeing a very smaller area, but with much higher resolution. Then I am seeing, very small strip with higher resolution, but I can see that strip anywhere. While here I am seeing 141 kilometer with a slightly poorer resolution, that is 20. Earlier, this one is 25.8 meter resolution. This is 23.5 meter resolution, and this is 740 kilometer area. So this is, earlier it was slightly different inside 1 3D, but otherwise it is similar. Only thing is you have done some changes so that this is much more efficient way of doing things, and we have achieved this. So multiple, this is called nesting. In smaller area, suppose I will see a larger area. I will find out what is the area of my interest. Then I will see with, say, this 23 meter, is it good enough? If it is not good enough, I will see much smaller area, maybe 11-12 kilometer area. But then I will see on 70, I can scan that area on 70 kilometer strip anywhere, and I will see that small area, and I will transmit that data so that I can see the details. Now, after that, I told you that we have a Cartosat 1. Cartosat 1 was launched on May 5, 2005. You can see there are 2 cameras here, and this is single camera. You can hear how the light path. There are 3 mirrors, 1, 2, 3. Primary mirror, secondary mirror, tertiary mirror. It reflects and it goes to the sensor. So here 2 cameras are there. One you can see is looking up, other is looking down. Up means when you make it look down, one is looking ahead and other is looking behind. So you are taking picture from 2 views. One is ahead, about 26 degree ahead, other is about 5 to 6 degree behind. So when you take picture like this, you can generate 3-dimensional picture, or say whatever stereo pictures very fast. Here you can see that resolution of 2.5 meter. It has a strip is about 27-30 kilometer. You can this base to height ratio tells you what is the angle. Means you can, what it says is that you can, what is the height resolution you can do compared to the resolution of, suppose I am seeing 2.5 meter resolution, then what is the vertical resolution that this base to height ratio tells you. We will not go into the detail, but it tells you what is the vertical resolution, and this is normally kept so that similar ratios, height also you can differentiate with similar resolution as you can differentiate on the ground the pixel. And then data rate, weight, all those things are given, which are not very important to us. I will not go into. And then here, these are detailed specifications. We are not going into detail because this, what happened is that my talk was day after tomorrow. For that, I was to remove some slides from here because I had collected so many slides and put only those slides which were important. But yesterday evening, Santoshi told me that because of certain reasons, Lal Saab, I think Lal Saab, isn't it? Lal Saab was to give a lecture on launch vehicle. He will not be able to do that today, and I have to do. So some slides are useless. You can forget them. We'll go to next one. This is Cartosat 2. Cartosat 2 gives a resolution of, it was launched as if you remember right, I was saying that we went to better than 1 meter, that is 0.8 meter in 2007. If you remember those trips from 1 kilometer, how we went to 0.8 meter. So this is the satellite which took the pictures of 0.8 meter resolution very fast. Again, this also used step and stair. Only thing is that in this step and stair, our gaps were smaller, while in Cartosat, in both Cartosat 1 and specifically in TS, the gaps were larger because the ratio there, if you remember, the ratio of the satellite velocity to line of velocity was 6. Here that ratio is 3. So our gaps are smaller and you can take pictures with a higher resolution. Here you can take pictures with 0.8 meter resolution and much higher signal to noise ratio. That is how we have improved from TES to Cartosat 2. Then we designed a new sensor, used the same telescope as Cartosat 2, but we changed our sensors. We, instead of, to increase the integration or exposure time, you can do another technique. There are special type of sensors available, which are called time delay and integration type of CCDs. So using those CCDs, you can make pictures with higher signal to noise ratio with a smaller instantaneous exposure time, because you have large number of strips, and those strips, when they come directly over the same strip, you take another picture, third picture, fourth picture, and those pictures are added. So our signal to noise ratio improves. So here this satellite Cartosat 2 CD did not do that step and stair. You can continuously, without any loss of data, continuous long strip you can do. Here you can see, I can take strip like this, or I can take, say, these are 2 strips, one strip here and other strip here. Then there will be gap. But if I take continuous strips, there will be no gap. Or I can take here. These are called different modes. I can take a square picture here. So I can move a satellite and take different pictures in a different orientation depending on which target I am interested in. So this is a very flexible satellite. It is called Agile Satellite. A lot of agility is there. And with that agility, I can take pictures any way I like. Of course, there will always be limitation. But most of the modes in which I want to take picture, I can do using. These are some of the pictures. You can see the details. Vidhan Sauda and all that. Then Cartosat 3 became, which has a resolution of 28 centimeter, and this was launched on November 27, 2029. Now, this completes our optical. We call them optical satellites because they operate up to a maximum optical SSO satellite. That is Sun Synchronous Orbit. Sun Synchronous Polar Orbit satellite we are completing here. Now, here Cartosat 3 series, of course, same, which I told you, that 28 centimeter resolution. We have another satellite which tomorrow, similar to this satellite, RISAT, it is a C-band radar, and it operates in different modes. Again, you can see 3 meter with 30 kilometer swath. Same satellite, you can change the mode then 12 kilometer with 30 kilometer swath, 25 meter with 120 kilometer swath, 50 meter with, so you can see differently, and you can see here that we are looking slightly slant. That you have to do. I don't know the details how. I'm not expert in radar satellite, but you have to look slightly slant to get the correct resolution both along the track and across track. So in the range and the other direction, you can get correct picture. So this is RISAT. We are going to launch that. Now we have INSAT series. INSAT series, this is INSAT 1 satellite where you had visible and infrared sensors. That is, infrared sensor measures the sea surface temperature, and visible sensor measures the clouds and the motions of the cloud and other ground features. So from that you can derive atmospheric parameter. Then finally we went to Kalpana satellite. Kalpana satellite was also similar. INSAT satellite, which we saw, had both communication, because weather satellites are geostationary satellite. So you can put some communication. This was our earlier bought out satellite in IRS1, INSAT 1 series. So we had to optimize our profits or optimize our utility of the satellite. We had some communication, some weather, both instruments were there. But then as our weather instruments became more complex and much better resolution, then we went for satellites which are doing only weather work. Kalpana was our first satellite, but it was a small, because what happened is that our INSAT 1D was ending its life. We did not have another satellite ready at that time. To our INSAT 2A and 2B, they were short-lived satellite. There were some problems coming. We were not able to get infrared imagery as good as we should be getting. There were some compromises. And IMD did not want those compromises. So within 1 year time, we developed only this Kalpana satellite, a small satellite which we call 1 ton satellite. That is the weight of the satellite. It had the same VHRR which was there on 3A and 3B. Only thing is that we designed that satellite, and instrument we made, everything was done in about 1 year, and that too from left out component, because we did not have the component. We had used up all the components in 3A, 3B. I mean 2A, 2B. 3A was also almost made, but only thing is it had some problem, so it was still on the ground. So we did not have component. We refurbished some component, we salvaged some component, and we made. And this is one of the satellite which of our atmosphere, for atmospheric purposes. This was weather purposes. This was the satellite which gave about 12 years of life. After that, 3D is also working and 3DR is also working. But this is one of the longest living satellite of ISRO. Of all the satellites, it is not the longest living, but one of the longest living satellites. I think recently 4A also lasted for 12 or 13 years, even when its life was only 10 years. So this is 3DR, where we have not only imager, but we have imager here. This is imager, and this is imager bottom, and this is sounder. How I can tell? They look similar. Only thing is that here you can see there is a separate cooler. So that cools the wheel. This is inside a filter wheel. So you can take picture in different bands. How you take? Because here in this you are taking pictures in 19 bands. So that is called atmospheric sounding. What you do is that you measure the radiation from different layers of atmosphere. So that how you do it? By putting a special type of filters. If I put one filter, I will be measuring at a certain level. Maximum radiation will be coming from certain level. I put another filter at certain different level, third level, fourth level. Of course, other locations also input will be coming, but that will be, so I can deconvolve all that, and I can measure radiation in a given band coming from different layers. So I can generate a vertical profile of atmosphere. That is called vertical profile generation of atmosphere, is called atmospheric sounding. So this is that sounder instrument which has a 19 channels. Only thing is it has a filter wheel, so it does that sequentially. While this imager doesn't have a filter wheel, it has bands which are there. You can see it has 6 bands, and all bands are simultaneously taking picture with 1 kilometer resolution for our visible and shortwave infrared, and about 2 kilometer resolution for 2 to 2.5 kilometer resolution, 4 kilometer resolution for thermal infrared, because you are measuring both 10.5 micron to 11.5 micron meter and 11.5 to 12. These are the bands. So because why you are taking picture in two band? Because when you take picture in two nearby band, you can avoid the atmospheric effect, and water, which is a black body, you can measure the sea surface temperature. From sea surface temperature and other parameters, like from our ocean set, we can measure the algae. Means algae is the food for fish, and temperature is how comfortable the fish will be there. So from using both this data, you can tell the fishermen where they will get good catch of fish. So they can go there, and now we have Navik. So using Navik, you can take the data from VHRR or from Kalpana and instead 3D, 3DR, and then take the data from our ocean set, combine that data, do the interpretation that is done by scientists, and they tell them longitude and latitude where they have to go so that they will get the good catch of the fish. So that is how satellites are helping in day-to-day life. Here we are seeing the band and various resolutions. I told you that here TIR1, TIR2, that is 10.5. Of course, I told you 10.5 to 11.5, but it is 10.3 to 11.3. So you can get rid of atmospheric effect, and you can measure very precisely every 4 kilometers. The pixel is but for ocean it is good enough. Temperature doesn't change that fast. So every 4 kilometer by 4 kilometer area, you can get 1 pixel and find out what is the exact temperature there. Similarly, water vapor also you can find out how much water vapor is there in a given column. Knowing that water vapor and other parameters, you can find out how whether you will feel very hot because of humidity, or whether there is a possibility of rain there. All those predictions are done using this data and atmospheric models. Here is the picture. You can see here India is almost centered here, and you can see this is about 81 degree north, 81 degree south, and here you can see all the way up to Middle East, and here you can see even these areas. So this is 1/3 of the Earth globe picture. Of course, it looks like a disk, but it is a globe. It is curved, and then because of curvature, we are doing the projection because it is a 3-dimensional picture, but we are projecting on a 2-dimensional map. So, and that is done properly. Mapping techniques are there. Using that, you can do. So that was the picture of one band. This is shortwave infrared band. Now GISat, I will not talk much of GISat because it was not successful, but it was supposed to do agriculture type of mapping, which is 23 meter, 50 meter type of resolution, 500 meter type of resolution from say, but it is available 24 hour all over India, 1/3 of the India. So that was, but at the launch there were some problems. Very recently it was launched on GISat 2, GSAT, okay, our GSLV Mark 2. In GSLV Mark 2, when it was launched, there was some failure. Third stage did not ignite, or ignite and it did not work. That is cryostage, and this was not successful. So I will not go into the details of this. But here you can see that we had how resolutions have improved. I have shown you earlier. This is a snapshot picture. We started with a resolution of about 1900 microradian, and we have reached in Cartosat 3 a resolution of 0.55. In so many years it was working. These are the types of resolution. You can see that about 4,000 times better resolution, like 3,800 times better resolution satellites. We started in 79, 70, and by 2020-21 we have improved our resolution by a factor of about 4,000, and then multiple here different type of optics are used depending on what resolution you want, what type of number of bands that you want, what is the FOV, total FOV what you want. So different type of optics are there. We will not go into the details of those optics. Now we will have a cursory look at our planetary mission. So one planetary mission was Chandrayaan. As you know, Chandrayaan 1 was launched on October 2, 2008. And these are the payloads. I will tell you 3 payloads which we discussed. One was MIP, that moon impact probe, because we wanted to put a probe on the surface of the moon. So we released that moon impact probe. Of course, it was a crash landing with Triranga that our tricolor on the south pole, we made it land. Of course, it was a crash landing, but anyhow, we can say that we also have landed on moon. There were some political implications of that also. We will not go into that. Then we added TMC. TMC is such that it can take it from 100-kilometer orbit of the around the moon. It can take picture with a resolution of better than 5 meters. And of course, moon meteorology mapper. You all know that our Chandrayaan-1 detected water, not only detected water, but even decided how the water is generated, how the water moves, where the water is, in which season, what type of water is there. And we launched this Chandrayaan-1 using our PSLV. You remember that I told you that PSLV can launch the satellite in a very low Earth orbit. You see, it is a sub-GTO orbit. It is 225 kilometer by 22,000. 30. We have not gone to. But then we used to make it more and more oval by firing the motor which is there inside our Chandrayaan. You fire at apogee, you will understand. By firing at perigee, you are increasing the velocity, means our orbit will become more elliptical. So elliptical means apogee will go farther. So we went on increasing the apogee like that, and then we made it in such a way that when moon is last, when it was here last, this yellow orbit, when it was here, we have to do it correctly. You see, timing. Our moon is here, but when we reach the apogee, moon also should. So precise calculations are done. You see, so moon is moving with its own speed. This is moving with its own speed. That is varying speed because it's an orbit. It's an elliptical orbit. So when our Chandrayaan-1 reaches there, moon is also there, and you fire the you do lunar capture, you do LC, and then you capture in the lunar orbit, which was originally 504 kilometer by 7,500 kilometer. Then slowly you circularize orbit, and finally, for collecting scientific data, we put in 100 kilometer by 100 kilometer orbit. Now, on the color band, where many instruments are there, where they were, you can see that our M3 was very near to infrared and visible, slightly beyond visible, but on infrared. Then we had mini SHAR, that is again synthetic aperture radar, which was in radio wave, X-ray, then gamma ray. There were so many of them. Will not go into the detail because it will consume. Here it shows how the moon mineralogy mapper. Moon mineralogy mapper was nothing but a spectrometer. You have large number of spectral bands. Now, why you need large number of spectral bands? Because I want to generate these type of curves. What are the signature? When I want to generate signature, if I have large number of bands, then I can see wavelength versus reflectance. I can generate full curve. And here it is waterized. So this molecule they detected. And this detection of this molecule, this is almost edge of, it was this moon mineralogy mapper. It was not going all the way up to this. It was going slightly. So you just detected. It was just lucky. But what we did is that we put another moon mineralogy type of mapper, our own mapper. This was NASA in Chandrayaan-2. And that now it is studying much better because you are going to much longer wavelength and you are doing much better resolution with a much better resolution, both spatial resolution and spectrometric resolution and larger wavelength. Here you can see how we made a map of water on moon. So that is using that moon mineralogy mapper. Then we have Mars orbiter. All of you know that you have heard a lot about Mars orbiter. I will not give you many details, but I will tell you why it is very important that we launch Mars orbiter when we have to launch. See, we launched on November 5, 2013. Why? What is so special? If we miss that, we will have to wait for 26 months. Why? It is here, you can see. See, there should be a particular angle between Earth, Sun, and Mars and our satellite. Unless that particularly Earth and Mars is very important. Only when that there is a particular angle. See, that angle I am drawing from the center of the Sun. So, or center of the Earth, or center of the Sun, wherever you draw. I draw an angle. I will draw it from the Sun because it is easier. So, with respect to Sun, our angular velocity of Earth is about I told you 1 degree per day, about 0.98 degree per day. With respect to Sun, it is moving. Then Mars is moving 0.52 degree per day. So that means, what is the differential velocity? Differential angular velocity is 0.646 degree per day. 0.46 degree per day. Now, whatever geometry I have, that geometry will repeat when I cover total 360 degree. When I cover 360 degree, so what is the time? 0.46 degree difference will change. Difference, I am talking of difference. Difference is 0.46 degree per day. So total difference again becomes 360 degree, means same geometry. That will become after 779 days. And that 779 days is 26 months. So I have to wait for 26 months. That is why this date was very sacrosanct, and we launched it. Then we had that mission. There you can see how it went, how finally, again here also, when you are releasing that your spacecraft is going in this trajectory, your Mars is going, and you are hitting a bullet. When you are hitting a target is not there, but you have to assume that when your velocity of your bullet will be such that when the bullet reaches at that location, Mars also will be that location, so that you can capture it. That is how we successfully did. This was the first time we did, and we achieved that. No other country had done that. It was a different type of payload. Methane sensor was there. Then Mars. Then we have AstroSat. This is an astronomical satellite where it is a multi-band satellite. You can see the different type of band. Then we have Chandrayaan 2. Chandrayaan 2 was very. It had some instruments. It had orbiter. It had lander and rover. Of course, lander and rover, we were not successful, but orbiter is still orbiting, and it is doing a job better than what Chandrayaan orbiter. Chandrayaan, whatever was moving in 100 kilometers was orbiter. This is also orbiter, and it is taking pictures. Of course, lander we were not successful, but similarly, this was launched because this was much heavier. We launched it using GSLV Mark III. So these are some of the details. I will not go into the details. These are the payloads, and those payloads everybody has heard. And I think I will now stop it here. Thank you very much for your patience. I think it is quite long. I am also tired, and you must be
Yes.
must have been bored listening to me. Some of them who might have gone to sleep. It is always better to sleep rather than disturb. Thank you very much.